In the last video we showed how to run a batch of CrystalGrower simulations on Condor with scripting, and we saw that we can run hundreds or thousands of simulations with just a few scripts. But the issue then arises, how are we going to analyze all of these results in an effective way? So as we're looking at crystal morphologies, a sensible choice for numerical data to analyze would be aspect ratios between certain Miller indices. If you run CrystalGrower in color mode, all of the length data between pairs of facets that you've chosen will be saved in the simulations parameters file for each of your simulations. So if we open up one of those in a text editor quickly, and scroll down to the bottom, we can see that we have all this data in the file. But you don't want to have to go through and manually copy and paste this out of thousands of simulations. So this is another point where scripting is going to be useful. So in a previous video, I showed the command grep. So grep searches for a string in your text files and spits out the whole line that that string appears on. So if I type grep and I'll search for nanometer, and I'll look in my simulations parameters file, you'll see that it spits out all of those lines. So what we need is some script that'll pull all that data out and format it in a way that we can somehow calculate aspect ratios easily from, perhaps with another script or a program. So I've written a program that can do that and formats your data into something that you can read into Excel, calculating aspect ratios between the lengths that you've chosen. But first of all, we need to get this data into a nice format for that program. So here I've written a grep script which will create a file for every single time the variable in the outer loop will increment. If we want to plot things against each other on a 2D plot, we want to make sure only one parameter is changing at a time. So if I open my grep script, you can see that it's quite a short script again. It's fairly simple to follow. So I have a variable called counter, a variable called counterFile, and a variable called k, and I'm setting them all to 0. Then I have a loop where j is my loop counter, and the number of times the loop executes is equal to the number of simulations that I've run. So there's 25 simulations here, 0 to 24. So within this loop, every time j is incremented, the counterFile variable is incremented. And the value of this counterFile is checked if it's divisible by 5, because my inner loop ran 5 times. So every 5 simulations, I want to save a separate file containing the length data, because at that point my first variable has also incremented. So I'm going to have 5 files with 5 entries in them. So that will be a value of energy 1 with 5 different values of energy 2. Then energy 1 will increment, the same as it did in our previous script, and then we'll have the 5 values for energy 2 again. And this will repeat for every value of energy 1, so we'll end up with 5 files. And all this k variable here is keeping track of is what number to assign that file that's going to contain all these lengths. So the command echo is going to print a value to the correct file. So it's going to print the number of the simulation. So this will be a number between 0 and 24, depending on where we are in the loop. And then it will output the return of the grep command searching for nanometer within the correct simulation parameters file. And it's going to append that, that's what the double greater than symbols means, to that file numbered by k, ratios.txt. And then it's going to print a new line between each of those entries. So let's try running that script. So we'll type /grep script all lengths.x, and then if we type ls, you'll see that we have some new files going from 0_ratios.txt up to 4ratios.txt. So let's make a new folder to save these in. We'll call this folder ratios. And we'll move everything with the word ratios.txt into that folder. And then we'll navigate into that folder and type ls. We now have 5 files which we can use as inputs to our aspect ratio program. I'll provide a link to download this program in the description. So if we have a look at the format of this file, you'll see that we have the simulation number, all the length information from the simulation parameters file, and then a new line between each data point. So we have 5 files with 5 data points each. And each of those files will be one plot for one value of energy parameter 1 against 5 values of energy parameter 2. So we'll be able to plot with a fixed value of energy 1 how the value of energy 2 affects the aspect ratio of the crystals. So let's try running this program. The first thing we need to do is download these files to our machine. So I'll use FileZilla to download my files to a folder that I want. So that's my tutorials folder, high throughput, and I'll download my simulation results from Condor. So if I go into that ratios folder, I'll download those 5 ratios files. So this is the small C++ program I've written here, which calculates the aspect ratios from these files. So now let's run this program and see what kind of prompts appear. So it comes up with a few questions. First one is, how many files would you like to process? So your outer loop number. So in this case we have 5 files. What is the root name of your files? So the file name after the number value. So these are called ratios.txt, so we ignore the underscore. How many indices are in your file? So if we go in here, we can see we've got 12 indices here. So if we type 12 here. How many data points would you like to plot? So how many data points are in each of your files? So in this case, there's 5 because we did 5 by 5. What is your starting energy value on the x-axis in kcal per mole? So it asks you this so it can format your axes correctly in Excel. So we started at 2.0 kcal per mole, and our energy spacing was 0.1 kcal per mole. So this just lets it fill in the x-axis column for you. And it'll ask the same then for your y-axis. So in this case it was 2.0 as well, and the spacing was 0.1 kcal per mole. Then it will tell you a bit of information about the files that it's read in, and it will then ask you how many ratios do you want to plot. So generally I keep this number a bit low because once you start calculating the combinations between things, it increases the number of files dramatically. So we'll stick with 3 for now. And that then tells you how many combinations of aspect ratios it's going to plot. It will plot the aspect ratios between all the lengths that you choose, so every combination. So with 3 lengths, you get 6 possible combinations. Then it lets you choose the lengths that you want to calculate the ratios for. So let's say, for example, I want to look at the 100 length, which in this case is number 12. So I'll type number 12. Then I can choose another length. So perhaps I'll choose the 010 direction, so that's number 11. Then let's say I want to look at some of these other indices. So let's say one of the 111 set. So let's pick number 6, which is the -1, -1, direction. Then it'll quickly calculate the aspect ratios and close the window. So if we go back to our file, you can see we now have a set of CSV files. So these can immediately be opened in Excel and put into a spreadsheet. So just a brief discussion of the naming system here. Ratios processed means it was following the same order as your files. So it will be energy 2, or the parameter that's in your inner loop of your simulations, on the y-axis. 0 ratios transposed is flipped around. So it will be the parameter in the outer loop of your simulation, or variable 1 in our example, on the y-axis. Then we also have a set here of 3-dimensional plots. So these will be formatted in a way that you can just quickly plot a 3-dimensional plot in Excel. So let's open one of these and have a look. So if we open this 0 ratios process file, it's going to open in Excel. And you can see we've got the energy 2 kcal per mole going up to 2.4 kcal per mole. And we've got all the aspect ratios between the lengths that we've chosen. Now if we open the transposed file, you'll see that the first row on each of them will match each other. That's because they'll be taken from the same simulation, but the ordering will be different because you flipped around which species is on the y-axis. So now let's look at the format of one of the 3D plots. So these 3D plots are just combinations of the 2D files that I've just presented. So you'd have the same result as if you went through and copied and pasted each of these columns together onto one worksheet. It's fairly simple to do when you have only a small number of simulations and a small number of aspect ratios. Once you start looking at lots of simulations, you want an automatic way of doing this. So if we wanted to plot this as a 3D plot, we can just select our data, we can say Insert, Chart, and we can choose a surface plot. And we have a nice quick three-dimensional plot of our simulation data. It doesn't look that impressive with this example, but when you've got thousands of simulations turned into a three-dimensional plot, you can really map out the energy landscape for these parameters. If you're plotting lots of graphs, it's really useful to record or write macros in Excel to speed up the plotting process. So I've written a macro which can create one of these plots quickly for me, which I'll make available too. You can edit this macro to make the graphs that you want, but it can save you quite a bit of time. So I'll just run this macro now quickly. So you can see it's plotted the same data, but it's also added some labels to the axes, which it's pulling from these boxes up here. And it's also got rid of the grid lines and coloured the axes differently. And it's moved the location of the legend. Those are things you'd have to do manually if you didn't have a macro to do it for you, so it can save you quite a bit of time. You can also couple this macro with some loops. So if I had all 6 3D plots in this one workbook, I could write a macro which goes through each sheet and plots a graph for each one of those automatically. So what if I wanted a series of 2D plots instead from the processed and transposed files that we've generated? And we can do that again with some macros. So if I go to the folder containing all my 2D data, I can make another Excel workbook. I'll just call this one processed, for example, because I'm going to combine all the processed files into one workbook and plot a graph for all of them on each worksheet using a single macro. So if I open this empty workbook, I'll click Developer, I'll go to my macro, and I'll use Combine and Plot No Trend Lines. Again, I'll make this macro available. So this macro is in 2 parts. The first one combines all CSV files into one workbook, and the second half plots graphs for all of the data in the workbook, going through one sheet at a time. So I need to navigate back to my CrystalGrower folder, where all my data is stored. And I only want to get the processed files, so I'll search in the search bar here for star processed. This will find me everything that's got the word processed in it. I'll select them all, press open, and you can see it's read all of them in, saved them on separate worksheets, and then plotted some graphs using the data up here. You can modify this macro to just plot things as points, or you can even get it to plot trend lines as well. But Excel macros are really powerful tools that can save you a lot of time when you're processing data. Even if you're looking at experimental data, for example, comparing X-ray diffraction patterns, knowing how to use macros can save you a lot of time in the long run. This macro is actually general, so it doesn't just work for aspect ratios. It actually plots the first column on the x-axis against all of these components on the y-axis. So you could actually use this for any other situation where you want to plot x versus y and you have lots of y columns. So I hope that's shown you an example of high throughput processing of lots of simulation data using some programs and some macros. I've provided the macros I used in this video as starting points, but these can be edited for your own purposes.